Welcome to Root Research, where we decode science in plain language. Today we're diving into a wild idea made real. Robots so small they can swim like microbes, sense what's happening around them, and follow a program for months. Shown by Marc Miskin and team at Penn, working with the tiny computer experts David Blaauw and Dennis Sylvester at the University of Michigan, plus collaborators. Let's start. What if robots stopped meaning metal arms and started meaning tiny helpers, inside places we can't reach? Here's the elevator pitch. If you can build a robot that's about the size of a microorganism, you can send it into environments where normal tools fail, like the narrow channels of a lab on a chip, the microscopic landscape around cells, or tiny manufacturing spaces where human hands and even regular machines are basically clumsy giants. And the big flex in this work is not just that the robots are tiny, it's that they can sense, process, and act on their own without a tether or a big external controller telling them what to do every second. So how small are we talking, and why is that a big deal? The team reports robots that are barely visible to the naked eye, measuring roughly 0.2 of a millimeter by 0.3 of a millimeter and only about 0.05 of a millimeter thick. That's smaller than a grain of salt territory. More like something that could sit on the ridges of your fingertip and look like a tiny speck. At this scale, the rules of movement get weird. You don't swim the way a fish swims. Water feels thick. Marc Miskin describes it like trying to move through tar. So the usual robot tricks, gears, joints, spinning props, become a nightmare. How do you move through tar when you're almost too small to see? This is one of the coolest parts. Instead of pushing themselves forward with moving parts, these robots basically push the liquid around them. Miskin's group uses an approach where the robot creates an electric field that nudges ions in the surrounding water. Those ions shove nearby water molecules, and that produces a force that moves the robot. No tiny flapping tail, no microscopic propeller. Just a clever physics hack that turns the environment into the engine. And because there are no moving parts in that propulsion system, the robots are described as durable and easy to handle with simple lab tools like a micropipette. And they can keep swimming for a long time. Okay, but where does the brain fit if the robot is basically a speck? This is where the Michigan crew comes in. Blaauw and Sylvester have spent years shrinking computers to ridiculous sizes, and here that work becomes the missing puzzle piece. The robot doesn't just move, it carries a tiny computing system that lets it run a program and respond to inputs. And the power budget is almost comical. Blaauw's team had to run the program on about 75 nanowatts, which he frames as about 100,000 times less than a smartwatch. That's like trying to run a whole day's plan on the energy you'd normally waste doing basically nothing. So they didn't just shrink hardware, they also shrank the software thinking. Blaauw describes reworking the program instructions so that what would normally take many steps could be condensed. Basically inventing a shortcut instruction so the code could fit in tiny memory. How do you power and program something that small without plugging it in? Light. Literally. The robots use solar cells to harvest energy, and some of those solar cells also double as optical receivers. That means light isn't only food, it's also a messenger. The robots are described as being powered and programmed by light pulses, and each robot has its own unique identifier, so you can send one set of light instructions to robot A and a different set to robot B in the same batch. That detail matters because it's what turns a pile of tiny specks into a team. If every robot can have its own role, you can imagine dividing labor. One group scouts, one group measures, one group follows a boundary, one group signals back. What can these tiny robots actually sense right now? temperature, yeah, but and surprisingly well. The batch described in Science Robotics includes sensors that detect temperature differences down to about 1/3 of a degree Celsius. And they don't just measure temperature as trivia. The researchers describe using temperature as a proxy for what's happening biologically, because tiny changes in heat can track cellular activity. Then comes my favorite, this sounds like science fiction, but it's not part. How do they communicate what they sensed? They wiggle. Blaauw points out that the robots reported temperature information by wiggling in a way compared to the honeybee waggle dance. It's not Wi-Fi, it's not Bluetooth, it's motion as a message. At tiny scales, even that is a smart choice. Simple, cheap, visible under a microscope. Why would medicine and manufacturing care about a robot doing a tiny wiggle? Because the big vision is not one robot does everything. The vision is lots of cheap robots, each costing about a penny, working together and lasting for months. In medicine, the team highlights ideas like monitoring the health of individual cells. Think about how most medical tests work today. We take a sample, measure averages, and hope the signal is strong enough. But biology is messy. The most important thing might be happening in a small patch. A pocket of inflammation, a cluster of stressed cells, early changes that are local and easy to miss when you average everything together. Robots at microbe scale could, in principle, hang out in those tiny zones and build a map of what's happening where. In manufacturing, they point to constructing microscale devices, the kinds of tiny structures used in sensors, microfluidics, and other tech where assembling or inspecting small features becomes painfully difficult. If you can program swarms to move in patterns, even coordinated like a school of fish, you can imagine them acting like living tools for tiny assembly lines. Let's make it real. What's a plausible day-in-the-life scenario where this actually helps? Picture a future hospital lab looking at a biopsy sample, say suspicious tissue where doctors want to know whether a small region is acting normal or hyperactive. Right now, you stain tissue, image it, maybe run genetic tests. Powerful tools, but they're often snapshot-based. Freeze time, analyze later. Now imagine instead they sprinkle in a swarm of these light-powered micro-robots. Each robot is assigned a job through light pulses. Some drift across the sample in a grid pattern, others patrol edges, others focus on hotspots. As they move, they measure tiny temperature differences. Not because temperature is the diagnosis, but because it can act like a quick proxy for metabolic activity. If one tiny zone consistently shows a different heat signature, the robots waggle more in that area. A simple visual cue to the technician. Hey, look closer here. Then the lab uses that cue to decide where to zoom in with high-end imaging or where to run more expensive tests. In that workflow, the robots aren't replacing doctors. They're acting like microscopic scouts that help aim attention and resources at the most informative spots. That's the vibe. Not magic, not instant cures, just smarter, finer-grained information, gathering at a scale where humans usually struggle. What makes this a real milestone instead of a cool demo? Miskin basically frames this as robotics finally breaking through a long stall. The electronics world kept shrinking, but robots couldn't keep up because autonomous motion at microscale was brutally hard. He describes it as a challenge that stalled progress for decades. Here, the pairing of Penn's propulsion with Michigan's tiny computing turns micro devices into something closer to a true robot. Sense, decide, act, and the team doesn't oversell it as "we're done." Miskin literally calls it the first chapter. The foundation is what matters. Once you can fit a brain, sensor, and motor into something almost too small to see, the next chapters can add more memory, more sensors, faster movement, tougher environments. So what's the main takeaway you should remember when you close this video? Blaauw, Sylvester, and Miskin, with co-first authors Maya Lassiter and Jung-Ho Lee and a broader team, show that fully programmable autonomous microrobots can be built at near microorganism size, powered and programmed by light, moving via ion-driven propulsion, sensing temperature with fine precision, and even signaling information through motion. The headline outcome is simple. Robotics just got a new scale to play with, and that scale could change how we monitor cells, navigate tiny lab environments, and build or inspect microscale technology. Big thanks to the scientists behind this work and to everyone pushing engineering into that "how is this even possible" zone. If you like what we do, subscribe and drop a comment with the next paper or topic you want us to decode.